Morning, everyone. First off, I want to extend a big thank you to Lidar CANEX, GoGeomatics team for hosting this fantastic event and for giving me the opportunity to speak today. Also, a huge shout out to all the presenters from yesterday. There were some incredible discussions on the current state of LiDAR and its advancements and its applications across industries. So yeah, I'm happy today to present to you on the redefining possibilities with RIEGL's multi-model TLS sensors, so the terrestrial side of LiDAR. So if we can get started. Yeah, for those of you who may not be familiar, RIEGL is a global leader in LiDAR technology, specializing in high-performance laser scanning systems. With over 40 years of innovation, RIEGL designs and manufactures a wide range of LiDAR sensors, covering applications from airborne and unmanned to mobile and terrestrial scanning. Our systems are known for their precision, reliability, and advanced waveform processing capabilities, so making them an effective choice for professionals in surveying, engineering, and the overall geospatial industries. We provide turnkey survey solutions, OEM products and components, as well as service and support along the way. Today, I'll be focusing on the terrestrial side, terrestrial laser scanning, or TLS. In my opinion, TLS has seen a significant increase in demand over the past decade, driven by its ability to capture highly accurate, high-resolution data for applications such as construction monitoring, mining, forestry, you name it. Like, especially when our world is ever changing at a very fast and complex rate. Before diving into like the real world applications, I'd love to introduce our suite of TLS sensors. So here are some of the terrestrial laser scanners that RIEGL offers. Each of these models is designed to capture millimeter accuracy and millimeter point density. The main difference between them lies in their range capabilities. Looking at their names, it somewhat represents the range of each model. Whether you need a compact scanner like a VZ400i here for smaller scale projects, or powerful systems like the VZ6000 for larger long-range applications, there's a solution for every project. And we'll go into more detail on this specific strength of each model. So on this scale, you can see the full spectrum from the VZ400i with a range of 800 meters up to the VZ6000 at 6,000 meters. Even though I said the names of the model reflect the range capabilities for each model, it's not always the case. With a well-positioned pose and with great line of sight, our models can see up to these ranges on targets with 90% reflectivity. So the 400i and the 600i are usually very similar in applications because their range is somewhat in the same ballpark. It's just that the 600i is one of our newest model. It has way faster scanning speed, 25 seconds for 6 millimeter point density at 10 meter scan. The bigger guys here, the 2000i and the 4000i 25, are used for larger scale projects like mine pits or large topographic and cultural heritage scanning. Even though like the smaller range models such as the 400i and the 600i have no problem scanning these large areas, it's just that you have to scan more poses as compared to these bigger dudes. The 6000 is our max range model, which can shoot up to 6 kilometers in range or even further based on the line of sight and target reflectivity, usually used for larger glacier and snow volume change monitoring. Now that we've seen the range capabilities of these scanners, let's dive into one of the key industries where terrestrial LiDAR is making a huge impact, civil engineering. So terrestrial LiDARs, with their ability to capture detailed and accurate data and access many spaces where it's hard for a mobile or UAV or other platforms of scanners, these TLS LiDARs bring forth new ways on how we approach everything from construction and surveying to infrastructure maintenance and urban planning overall. Whether it's for monitoring progress on large-scale construction site, or making sure that the safety and efficiency of the whole process of building this critical infrastructure, especially when everything's nowadays the project scope for infrastructure is getting more complicated. So I want to jump into a case study. One of the most well-known infrastructure in Toronto is the Gardiner Expressway underpass. Over the years, concerns have grown over the deterioration of the beams and pillars. So like these structure right here that supports the highway. This is a elevated highway that runs to the city's core. So making monitoring and maintenance extremely complex. And because of its deterioration, it's crucial that we get a very good assessment of the structural integrity before any renovation or planning takes place. So these screenshots here are data snippets of just a small part of the underpass. The full stretch of the underpass crosses highways, roads, and buildings are laid underneath them, and in blind spots that really need high fidelity data. So, like, given the complex layout of these infrastructure, a mobile system or an aerial scanning wouldn't make sense. It's inefficient, it can't get the job done, and more so, it's most all about the public safety as well. So in this case study, we use a VZ600i terrestrial LiDAR on the tripod here, and we scanned 2+ kilometers of the underpass in just 2 days, followed by half a day of processing, so tied down to control points, delivered sub-millimeter accuracy, and colorized data for clear analysis. So as infrastructure projects grow, so does the need for efficient TLS solutions. And RIEGL scanners are built for this, high speed, precision, and optimized for demanding work environments. And beyond the hardware, RIEGL's workflow makes it easy to go from raw scans to final deliverables as well. So here is the beam scan footprint, kind of like a floor plan, but segmented, cross-sectioned to reveal all the pillars and beams that crosses this part of the underpass. So these are very accurate, millimeter precise, and you can get measurements between beams, between pillars, and you can actually see the surface deterioration of each beam if there's any concrete missing or any cracks. So this gives you a more concise, more clear view of the infrastructure. So it's better for engineers to make better decision, and it's more efficient. And with the rising demands of infrastructure, terrestrial LiDAR is definitely meeting this need. So now let's focus on indoors. So infrastructure outdoors is common, and TLS has been succeeding in outdoors for a while, but it's also important in indoor spaces as well, where terrestrial LiDAR scanning plays a critical role in capturing high precision data even in complex indoor environments where GNSS RTK is not available. So here we have the Gaylord Palms Emerald Bay Plaza in Florida. It's a stunning indoor space designed to feel like an outdoor environment. Inside, you'll find buildings, winding water features, palm trees, and small bridges, all under this kind of roof, ceiling net made of metallic bars and lots of sunlight. And this is the indoor scan of the plaza through the RIEGL TLS sensor. Scanning indoors present unique challenges compared to outdoors environments. So first of all, there's no GNSS, there's no RTK, so there's no positioning. And the second thing is obstruction of complex layouts, such as so indoor spaces sometimes have narrow corridors, multiple levels, reflective surfaces, and tight angles that make scanning more challenging. And same as outdoor, there's lots of constant movement, like people walking, doors opening and closing, and even sometimes lighting changes can impact the consistency of scans and colorization based on the time of day. So despite these challenges of indoor scanning, RIEGL's TLS handled the Gaylord Palms interior flawlessly, like thanks to the onboard registration with dual IMUs. So the system maintained a precise orientation matching, making data alignment up to a standard of 3 millimeter deviation of 3D space accuracy without any drift or mismatches. And as I said, that depending on the time of day, the lighting can be uneven. So as indoor environments suffer from these uneven lighting, RIEGL TLS also supports high-end external cameras integration, so like leveraging Sony or Nikon advanced photographic settings to capture consistent and true-to-life colors in different lighting conditions. And these capabilities make TLS ideal for scanning complex indoor spaces from hotels and convention centers to factories, plants, and utilities, basically delivering high precision data without much compromise. So after seeing terrestrial laser scanning is reshaping infrastructure both outdoors and indoor mapping, but its impact extends even further into the world of forensics. Okay, so just a disclaimer, this is just a demo set scan, and these are just dummies. So when investigating a crime or an accident scene, capturing every detail accurately and efficiently is paramount. Traditional methods rely on thousands of photos and manual measurements, but a single scan can preserve the entire scene in 3D down to millimeter accuracy in just a few seconds. For law enforcement, speed isn't just about efficiency, it's all about safety as well. The longer officers remain on an accident site, the greater their risk of secondary accidents, especially on busy highways. With faster scanning workflow, they can document the scene quickly and clear the road sooner, reducing dangers for both them and the public. But speed also impacts funding as well. I'm not too sure in Canada, but in the US, police agencies are graded by federal authorities on how quickly they can reopen highways after accidents. So faster scene documentation means better performance ratings, which directly affects funding and federal grant opportunities as well. And when it comes to forensic detail, fast is one thing, but precision is also a key. From large-scale accident reconstruction to the smallest pieces evidence, such as bullet casings, high-resolution scans ensure no critical detail is lost. Like with RIEGL's millimeter accuracy, small factors like bullet trajectory can be measured with confidence. Plus, with digital preservation, the scene remains intact for future analysis, providing investigators and courts with reliable, measurable evidence long after the site has been cleared. So just like VAR, like video assistant referee, soccer, this gives referee the ability to review and make more informed decisions after an incident in the field. The TLS scanning, that's the same for forensics. So by bringing forensics investigations into the digital age, TLS isn't just improving crime scene documentation, it's transforming the way justice is served. So I like to say that one picture equals 1,000 words, one scan equals 10,000 pictures. So we've seen how terrestrial laser scanning is transforming forensics and infrastructure, but its applications extend into industries like mining as well. In mining, accuracy, efficiency, and safety are also paramount. The TLS is perfectly suited for environments like this, offering very accurate 3D data to monitor mine sites, track stockpiles, assess tunnel stability, all while reducing the risk for workers. So let's take a look at how TLS is driving innovation in the mining industry. So this is a case study. We're using the RIEGL terrestrial laser scanning on a mine site, Lo Aguirre mine in Chile. So this mine is a copper open pit mine located in the region of Santiago and was voluntarily closed in 2000 to protect the surrounding environment. And that's part of its closure plan. The plan was to develop and to restore the land, like focusing on sealing leach dumps, land reclamation, and replanting vegetation. So a key part of the process was making sure the mine's infrastructure remained stable, especially the pit walls and the berms in high-risk areas. And then that's where RIEGL's terrestrial laser scanning stepped in. So what makes RIEGL's TLS particularly effective in mining? It's the dedicated mine monitoring workflow, which is specifically designed for long-term repeatable scans. This workflow includes the ability to set up scans in key locations, run them consistently, and track changes in the environment over extended periods of time. We have a reference scan, and you have a current scan, and this can be done in real time continuously. And by comparing the scans over time, engineers can identify changes in terrain and pit infrastructure, such as volume changes, movement of berms and sediments, or the development of cracks or slumps. This means that instead of relying on spot checks, engineers can track subtle shifts and early stage warning signs for potential hazards like erosion or subsidence, which would otherwise go undetected if there's no LiDAR scanner. Like this level of automation and precision offered by RIEGL's TLS and the mine monitoring workflow here make sure that all data is reliable, repeatable, and to help engineers make informed decisions and take proactive actions in real time. And as the demand for safety in mining operations increases, particularly in Canada over the past few years, TLS is becoming increasingly valuable. Stricter regulations and an emphasis on overall worker safety are pushing the industry to adopt technologies like the TLS. And RIEGL's TLS can help with real-time monitoring of infrastructure overall, helping detect potential hazards and supporting compliance with evolving safety standards. So besides the demanding presence of TLS in fields of mining and civil engineering, its capabilities extend well beyond those fields as well. Another key area where RIEGL TLS excels is in the environmental monitoring kind of sector, whether it's mapping forests, assessing coastline changes, monitoring riverbanks, or tracking glacier and snowmelt. Like RIEGL's TLS provides the precision needed to capture intricate details over vast landscape. So let's take a closer look at how this technology plays in the natural environment. So on the left, we have a colorized scan that captures the forested area with lifelike replication in RGB band. This provides a clear overview of the landscape and enables a general understanding of the forest health and structure. And on the right here, you see segmentation of tree data based on key features such as tree height, canopy width, trunk diameter or tree breadth, and overall size. And all this can be done through RIEGL's tree analyzer plugin workflow. So the tree segmentation is critical in forestry as it enables precise measurement of individual tree characteristics, which can be used to monitor growth patterns, assess forest health, and support sustainable forest management. And by isolating each tree, we can track changes in canopy coverage, detect diseases or damage to the trunk or to the parts of the tree, and estimate biomass with good confidence. Traditionally, forest assessments relied on plot level measurements. So like where field crew would manually survey small sample plots. And by measuring tree diameter, height, canopy spread, density, these measurements were then extrapolated to estimate the forest-wide characteristics. While this method has been a standard for decades, it has limitations. So like manual data collection is definitely time consuming and labor intensive, first of all. The second thing is sample plot sizes are limited, reducing overall accuracy. Measurements vary between surveyors, so leading to inconsistency and human error in forest modeling. When using the TLS, and specifically the RIEGL TLS, overcomes these kind of challenges. It captures the same detailed area measurements of the tree and more, with greater accuracy and at much larger scale. The high-speed automated gating process kind of eliminates user bias, ensuring consistent, reproducible data collection. This creates a more reliable and standardized data sets, leading to better interpolation models for estimating forest-wide attributes. This is extremely efficient and useful, whether for planting controlled burns, optimizing tree density, or evaluating carbon storage potential. It's high resolution, high accuracy data, helps forestry departments and researchers make better data-driven decisions faster as well. Another aspect of the environment is also for coastal mapping, especially along beaches where the landscape can be dynamic and constantly changing. Precision and real-time data capture are also essential. Like traditional methods like photogrammetry or handheld GPS systems can struggle to capture these necessary detail and accuracy across large areas, particularly in challenging coastal environments with shifting sand dunes, tidal waves, or uneven terrain overall. So TLS, like the RIEGL TLS systems, are suited to these applications also because of their flexibility in the platform integration. So whether mounted on a pickup truck here, or even on a boat, even on an autonomous small vessel, this TLS can easily be adapted to a variety of environmental settings. So in this example case study, the RIEGL's TLS is mounted on the tripod here on the pickup truck here, and it's operating in kinematic mode. So the vehicle drives along the beach coastline, the lidar spins and measures the sediment erosion of this slight hill right here along the coastline. And this setup allows the system to capture continuous high-resolution data throughout the entire drive. So you're talking 5 millimeter 3D point accuracy, just driving the stretch of this beach. So like while RIEGL also offers topobathymetric systems that offer valuable data for coastal mapping, especially when it comes to covering large areas, providing bathymetric depth information and sediment deposits and pre-deposits. RIEGL's TLS provides an additional layer of detail, capturing small-scale features along the coastline to where airborne systems lack in high resolution. For example, TLS can effectively capture fine intricate coastal erosion patterns with high precision due to its closer proximity to the ground and its ability to operate in a range of flexible platforms. And with Canada having one of the longest coastline in the world, faces high complexity due to its environmental features, and more so with our Canadian weather, TLS is in general, and RIEGL TLS in specific, with its precision, efficiency, reliability, and it's IP64 rated, which is dust and water resistant. It's an ideal tool for meeting the challenges of mapping and monitoring such a vast and varied coastline. As we move to one of the most impressive achievements in ice cap monitoring, it's also worth noting that RIEGL's TLS suite from the 400i to the 4000i 25 is already suitable for measuring ice and snow with remarkable precision. These systems have been widely used in ice monitoring applications, offering high resolution scans in remote environments. But when it comes to pushing the boundaries of what's possible, there's one that really stands out, the RIEGL VZ6000. So the VZ6000 is a truly groundbreaking piece of technology. It's offering up to 6 kilometers of range, making it capable for capturing data in areas previously out of reach for nominal terrestrial LiDAR systems. This scanner has only been deployed in select locations, and there are only about 12 of these sensors around the world. So the data it generates is nothing short of spectacular, providing an incredible detailed long-range view of ice caps and glaciers. So this image right here is actually in Antarctica, measuring the snow change difference and measuring how it correlates to sea level rise in the South Pole. So ice caps and glaciers are critical indicators of climate change, like holding crucial data about Earth's past climate, offering a window into the future. However, these kind of remote, harsh environments present significant challenges, both logistically and technologically, and in terms of access and data collection. And Yeah. So traditionally, when monitoring snow and ice, we relied a lot on mass balance stake networks. So it's a method where researchers would manually place stakes in the snow mass and at sampling points and revisit the same points over time to measure changes in snow depth. Like these measurements help estimate snow volume changes, but they were quite limited to specific points and required extensive interpolation to model the entire snow mass. So, like, why effective to a degree? This process was extremely labor intensive, time consuming, and posed significant risks, as researchers often had to navigate treacherous glacial and mountainous terrain to collect data. So, with the introduction of the terrestrial laser scanning, these challenges are somewhat overcome. A long-range TLS like the RIEGL VC6000 eliminates the need for manual stake networks altogether by providing a full area coverage rather than just point-based measurements. Instead of relying on scattered data points, uh, TLS captures the entire snow surface with pristine millimeter level accuracy and detecting even the smallest volume changes over time. And because TLS operates remotely, it also allows researchers to continuously monitor snow and ice dynamics at a safe distance, so reducing the risk associated with fieldwork. It can be deployed on daily, weekly, or monthly schedule, making sure that every surface change is recorded. And unlike traditional methods, which require interpolation to estimate snow volume changes, TLS data provides high resolution direct measurement of snow accumulation, melting, and redistribution of snow as well, offering unprecedented level of detail. So by using one of the most advanced long-range TLS system, researchers can now track glacier dynamics, ice shelf thinning, and surface changes without interruption. They're providing critical data to better understand the impacts of climate change. After sharing my insights on my experiences with TLS applications in today's age, I've put together this diagram to help break down where RIEGL systems really shine. Um, let me say upfront that every one of these scanners can technically handle all these tasks, but some models are just better suited for certain jobs, just based on the range, and that's what this visual is all about. So in the middle here, you've got the stars of the show, the VZ400i, the 600i, 2000i, 4000i 25, and the 6000, sorted based on range measurements as seen with this circular arrow right here. Starting with the bright red section, you have the as-built surveying. And so in this red section, it includes the as-built surveying, forestry, and forensics. The as-built surveying, think architecture, BIM, tidal surveying, and transportation. Like usually these kind of cases are good for 400i, and the 600i works best because they're very fast scanners and very versatile in these kind of scale. Next up is the purple section, the topography and the mining. We're talking DM, DTM generation, slope monitoring, flood mapping, volume changes. This is where one of the bigger, longer range guys come in, say the 2000i, 4000i, 25, depending on the project size and needs. Then we got the coastal mapping here in blue. We're mapping riverbanks, tracking sea level changes, monitoring sediment and biodiversity along the coast. The green is the city mapping. So like large scale urban planning, like remodeling transit lines, rail and road networks. So short to medium range lidars are good for these. And finally, the dark red area is for ice glacier mapping, mostly a job for one of the most powerful TLS sensors. But if it's a small hill or ski slope, 400i or 600i should work fine as well. Before I jump into Q&A, I'd like to share with you a video about the 600i. It's our flagship TLS, the Goldilocks of range and unmatched speed. How do the scanners handle the reflections in these environments? Reflections from snow, ice, water, window, glazing. These scanners handle reflection in these. So most of these surfaces that has 90% reflectivity uh, gets registered. And let me just start for the water, because our TLS is mostly in near infrared, so it gets mostly absorbed by the water. But since the snow and ice has different structure, the the physical properties is different, so it can still see snow and ice. There might be some multiple reflections due to like the refractions and reflectivity of the snow that causes multipath, but our systems can also filter out based on the reflectance intensity. So we have very complex advanced waveform manipulation that we can actually, for every beam that we shoot out, has a recording of the reflectance values. And yeah, it gives you the power to kind of filter out multipath, and gives you kind of the middle ground of snow, ice, and water features. Not water features, I mean. Will these scanners penetrate shallow water? Not really. The TLS, again, is near infrared, so it won't be able to penetrate through the water surface per se. Like at a slanted kind of incident angle, it wouldn't be able to. But if you were to hold the LiDAR above the water surface and looking directly at the water, it might have the specular reflectance from the water surface. So uh, it can, in some cases. It also depends on the lighting as well. So if you do it indoors, it's better to see the water than outdoors. I hope everyone is enjoying the presentation so far. If there's no questions, thank you so much for your time. Thank you so much.